Let's try this again using a more streamlined approach. Given sinusoidal AC voltage with an effective value of 48 volts at a frequency of 40 Hz across a 42 millihenry inductor, let's see if we can determine the effective value of the current through it and the relative phase shift between voltage and current. To somewhat complicate our streamlined efforts, let's assume this isn't an ideal inductor, but rather a non-ideal one that includes a noticeable amount of internal resistance, let's say 10 ohms. Using our given information, we can show that our Phasor equivalent of voltage V equals 48 volts at an angle of 0 degrees, since we're assuming it's the reference. Let's now determine the impedance of the non-ideal inductor. Recall from the series complex lecture available at the Big Bad Tech channel, a non-ideal inductor can often be visualized as the inductive portion in series with a small internal resistance, in our case 10 ohms. The resistive portion has an impedance of 10 ohms at an angle of 0 degrees. The inductive portion has an impedance of roughly 105.6 ohms at an angle of positive 90 degrees at our given excitation frequency of 400 Hz. Adding these two series impedances together, we find our non-ideal inductor has an impedance of roughly 106.0 ohms at an angle of positive 84.6 degrees. Given positive 84.6 degrees is still close to 90 degrees, means it's still primarily inductive. However, the slight tilt towards the real axis indicates there's a small resistive portion we need to consider. Given current lags voltage by exactly 90 degrees for perfect ideal inductors, can you anticipate by how much current will lead or lag voltage for this non-ideal inductor? Again, if you're skilled in the manipulation of complex numbers as I expect you to be, you should have an idea of what's coming next. Since we're being asked to solve for current, we divide the Phasor equivalent voltage V by the complex impedance Z to solve for I, the Phasor equivalent current. Doing so yields I equals 452.7 milliamperes at an angle of negative 84.6 degrees, where 452.7 milliamperes is the effective value of the resultant sinusoidal current, and it is phase shifted by negative 84.6 degrees, meaning it's lagging our agreed upon reference by 84.6 degrees. Given current through a perfect ideal inductor with no internal resistance with lag voltage by exactly 90 degrees, is it any wonder that current through this non-ideal inductor, incorporating a small internal resistance, only lags voltage by 84.6 degrees? It shouldn't be. Additionally, since the above conditions were established at 400 Hz, it is assumed the resultant current also has a frequency of 400 Hz. Note the Phasor diagram shows I lagging V by 84.6 degrees, super close to what we expect to observe for an ideal inductor. If you wanted to, you could derive the time-variant expression for voltage and current and plot them as a function of time. However, it's kind of unnecessary to do so, given all this additional information is just kind of useless filler compared to that conveniently expressed using the Phasor equivalent diagram. Let's tackle Ohm's law from a different angle. Given an ammeter reading an effective current value of 140 milliamperes through a 560 ohm resistor, let's use Ohm's law to determine the effective value of the voltage across it and the phase shift between voltage and current. Let's assume current has a frequency of 120 Hz. First, we need to express current as a Phasor equivalent. We know the effective value is 140 milliamperes, but we don't know the phase shift. Do we care? No, we don't. Since it's the only piece of pertinent information we've got about this circuit, let's just assume current is the reference. I equals 140 milliamperes at an angle of 0 degrees. Next, we need to express the resistance as a complex impedance. Doing so yields Z equals 560 ohms at an angle of 0 degrees. Now, since we're being asked to solve for voltage, we multiply the Phasor equivalent current I by the complex impedance Z to solve for V, the Phasor equivalent voltage. Doing so yields V equals 78.4 volts at an angle of 0 degrees, where 78.4 volts is the effective value of the resultant sinusoidal AC voltage, and it is phase shifted by 0 degrees. Additionally, since the above conditions were established at 120 Hz, it is assumed voltage also has a frequency of 120 Hz. Note the Phasor diagram shows I overlapping V, indicating they are in phase with one another in keeping with our expectations for purely resistive elements. Let's try the same permutation of Ohm's law from the perspective of a capacitor, only this time featuring a manky old 20 microfarad capacitor with a 5 kilo ohm leakage path in parallel. Let's say an ammeter is reading 215 milliamperes of current through it. Let's assume this current has a frequency of 60 Hz. First, we need to express current as a phasor equivalent. Again, we know the effective value is 215 milliamperes, but we don't know the phase shift. Do we care? No, we don't. Since it's the only piece of pertinent information we've got about this circuit, let's just assume current is the reference. I equals 215 milliamperes at an angle of 0 degrees. Next, we need to express the Mancke-Old capacitor as a complex impedance. Recall from the parallel complex impedance lecture, available at the Big Bad Tech channel, that a non-ideal capacitor can be visualized as the capacitive portion, in our case 20 microfarad, in parallel with the resistive leakage portion, in our case 5 kiloohms. At our given excitation frequency of 60 Hz, the capacitive portion is a complex impedance of roughly 132.6 ohms at an angle of negative 90 degrees. The resistive portion is a complex impedance of 5 kiloohms at an angle of 0 degrees. When combined in parallel, the whole non-ideal capacitor presents an impedance of roughly 132.6 ohms at an angle of negative 88.5 degrees. As with our non-ideal inductor, this non-ideal capacitor is still primarily capacitive, and that negative 88.5 degrees is super close to negative 90 degrees. However, there is a resistive portion that is accounted for by the slight skew from the perfectly vertical negative imaginary axis. Now, since we're being asked to solve for voltage, we multiply the phasor equivalent current I by the complex impedance Z to solve for V, the phasor equivalent voltage. Doing so yields V equals 28.5 volts at an angle of negative 88.5 degrees, where 28.5 volts is the effective value of the resultant sinusoidal voltage, and it is phase shifted by negative 88.5 degrees. Additionally, since the above conditions were established at 60 Hz, it is assumed voltage also has a frequency of 60 Hz. Note the phasor diagram shows voltage lagging current by 88.5 degrees. Or does it? Recall that current through purely capacitive elements is known to lead voltage by 90 degrees. Yet here Ohm's law is telling us that voltage is lagging current by nearly the same amount. Is there some error in our computation or a flaw in our previous assumptions? No, there is not. This diagram clearly shows voltage lagging current by 88.5 degrees, but it also shows that current leads voltage by positive 88.5 degrees, meaning that just like the dating scene in Iceland, it's all relative in nature. Recall that we initially assumed current was our reference waveform, given it was the only piece of information we had about our circuit of interest. There is absolutely nothing wrong with this assumption. Operating on this assumption, however, places all resultant calculations in this same plane of reference. Yes, it is true that voltage lags current by roughly 90 degrees for this non-ideal capacitive circuit when current is the reference. If, however, voltage is employed as the reference, it can be rightly said that current leads voltage by roughly 90 degrees for this non-ideal capacitive circuit. These are merely two ways of saying the same thing. Current is in front of voltage, voltage is behind current. Let's try the same permutation of Ohm's law from the perspective of an ideal 300 millihenry inductor. Only this time, let's include a twist. Let's say an ammeter is reading 90 milliamperes of current through it. However, this current is known to lag some previously agreed upon reference point, whatever it might be, by let's say 15 degrees. Let's assume current has a frequency of 80 Hz. First, we need to express current as a phasor equivalent. We know the effective value is 90 milliamperes, and we've been told it lags some previously agreed upon reference point by 15 degrees. Let's just go with this previously agreed upon reference point and call I equals 90 milliamperes at an angle of negative 15 degrees. Next, we need to express the 300 millihenry inductor subjected to 80 Hz sinusoidal AC as a complex impedance. Doing so yields Z equals roughly 150.8 ohms at an angle of positive 90 degrees. We're assuming this inductor is ideal in nature and includes no or negligible amounts of internal resistance. Now, since we're being asked to solve for voltage, we multiply the phasor equivalent current I by the complex impedance Z to solve for V, the phasor equivalent voltage. Doing so yields V equals 13.6 volts at an angle of positive 75 degrees, where 13.6 volts is the effective value of the resultant sinusoidal voltage, and it is phase shifted from our previously agreed upon reference, whatever it might have been, by positive 75 degrees. Additionally, since the above conditions were established at 80 Hz, it is assumed voltage also has a frequency of 80 Hz. Note the phasor diagram shows V leading the previously agreed upon reference by 75 degrees, and I lagging the previously agreed upon reference by 15 degrees. Is this scenario in keeping with your expectations about ideal inductors, in which current is anticipated to lag voltage by 90 degrees? It should. Previously agreed upon reference be damned, there is a 75 plus 15 degree phase shift between voltage and current does appear to lag voltage by exactly 90 degrees. Again, it's all relative, and you can bypass any confusion simply by looking at a phasor diagram. Let's tackle Ohm's law from a wholly new perspective. Given voltage and current readings, let's see if we can solve for impedance. Let's say a voltmeter is reading 12 volts across and an ammeter is reading 40 milliamperes of current through an unknown element. Let's assume both voltage and current have a frequency of 100 Hz. Additionally, we know the voltage and current are perfectly in phase with one another and that they simultaneously peak and valley. What type of component is this unknown element? What is its impedance? And what is its component level value? The answer to the first question should be easy if you can remember the three important takeaways from our general discussion like 3 minutes ago. Current through a purely resistive element will always be in phase with the voltage across it. In contrast, current through a purely capacitive element will always lead the voltage across it by 90 degrees. And finally, current through a purely inductive element will always lag the voltage across it by 90 degrees. Given our voltage and current appear to be in phase with one another, this unknown element is undoubtedly a resistor. Let's prove it with some math. First, we need to express voltage and current as phasor equivalents. We know the effective value of voltage is 12 volts, but we don't know the phase shift. Do we care? No, we don't. We may as well assume voltage is the reference. V equals 12 volts at an angle of 0 degrees. Now we need to express current as a phasor equivalent. We know the effective value is 40 milliamperes, but we don't know the phase shift. This being said, we do know current is in phase with voltage. Given voltage is a phase shift of 0 degrees, and current is in phase with it, we are free to assume it has a phase shift of 0 degrees. I equals 40 milliamperes at an angle of 0 degrees. Note the phasor diagram shows V and I overlapping each other, meaning they are in phase with one another. Now, since we're being asked to solve for impedance, we divide the phasor equivalent voltage V by the phasor equivalent current I to solve for the complex impedance Z. Doing so yields Z equals 300 ohms at an angle of 0 degrees, where 300 ohms is the magnitude and 0 degrees indicates it's entirely resistive in nature. Frequency has no effect upon our resistive impedance, and we are reasonably confident the component value of our unknown element is 300 ohms. Let's try a similar scenario, only this time including a reactive element. Let's say a voltmeter is reading 42 volts across and an ammeter is reading 34 milliamperes of current through an unknown element. Let's assume both voltage and current have a frequency of 55 Hz. Additionally, we know current is leading voltage by exactly 90 degrees. This is the dead giveaway that we're dealing with a reactive component, the fact that there's a phase shift between voltage and current. What type of component is this unknown element? What is its impedance? And what is its component level value? The answer to the first question should again be easy if you use the three general guidelines. Given current is leading voltage by 90 degrees, this unknown element is undoubtedly a capacitor. Let's prove it with some math. First, we need to express voltage and current as phasor equivalents. We've been given effective values for both, however we only know the relative phase shift between voltage and current. Which one is the reference? Voltage, current, or some other previously agreed upon property? Do we care? No, we don't. We can assume either of these properties is the reference. Given how the initial conditions are phrased, current leads voltage by 90 degrees, let's stick with this description and call voltage our reference with a phase shift of 0 degrees, and current is leading it by 90 degrees, meaning current has a phase shift of positive 90 degrees. V equals 42 volts at an angle of 0 degrees, and I equals 34 milliamperes at an angle of positive 90 degrees. Note the phasor diagram shows I offset from V by 90 degrees, meaning current is leading voltage by 90 degrees. Now, since we're being asked to solve for impedance, we divide the phasor equivalent voltage V by the phasor equivalent current I to solve for the complex impedance Z. Doing so yields Z equals 1,235.3 ohms at an angle of negative 90 degrees, or roughly 1.2 kiloohms at an angle of negative 90 degrees, where 1.2 kiloohms is the magnitude and negative 90 degrees indicates it's entirely capacitive in nature as we anticipated. Since we are being asked to solve for the component level of the unknown element, why don't you run down to the stockroom and grab yourself a 1.2 kiloohm capacitor. Don't waste too much time though digging through all the assorted bins, boxes, and bags because it doesn't exist. Recall the impedance magnitude of a capacitor is frequency dependent via the capacitive impedance formula 1 over 2 pi Fc. Given we know the magnitude, in this case roughly 1.2 kiloohms, and the frequency, in this case 55 Hz, we should be able to solve for the component level of the capacitor that satisfies this condition. Rearranging the capacitive impedance magnitude formula to solve for the capacitance and substituting in our given values, we find a capacitance value of roughly 2.3 microfarads. Problem solved. Let's step this up a notch with a similar scenario, this time including a minor complication. Let's say a voltmeter is reading 36 volts across and an ammeter is reading 52 milliamperes of current through an unknown element. Let's assume voltage and current have a frequency of 70 Hz. Additionally, we know that voltage is leading current. However, it's not leading by a perfect 90 degrees, but rather only 85 degrees. What type of component is this unknown element? What is its impedance? And what is its component level value? This isn't as easy as our previous examples, since our three general guidelines only dealt with purely resistive, purely capacitive, and purely inductive elements, and there are no explicit instructions for occasions in which voltage leads current by 85 degrees. This being said, 85 degrees is super close to 90 degrees. Perhaps one of these hats might fit better than the other two. Recall, current through a purely resistive element will always be in phase with the voltage across it. In contrast, current through a purely capacitive element will always lead the voltage across it by 90 degrees. Finally, current through a purely inductive element will always lag voltage across it by 90 degrees. By saying voltage leads current by 85 degrees, I am also saying current lags voltage by 85 degrees. The clear favorite for our present scenario is a largely inductive element. Most likely, this is a non-ideal inductor that includes a small resistive component. Let's prove this with some math. First, we need to express voltage and current as phasor equivalents. We've been given effective values for both, however we know only the relative phase shift between voltage and current. Which one is the reference? Voltage, current, or some other previously agreed upon property? Do we care? No, we don't. We can assume either of these properties is the reference. Given how the initial conditions are phrased, however, voltage leads current by 85 degrees, let's just stick with this description and call current our reference. I equals 52 milliamperes at an angle of 0 degrees, and voltage equals 36 volts at an angle of positive 85 degrees, meaning voltage is leading current by 85 degrees. Note the phasor diagram shows V offset from I by 85 degrees, meaning voltage leads current by 85 degrees. This being said, note the relative phase shift between voltage and current. The phasor diagram clearly shows I is offset from V by negative 85 degrees, meaning current is lagging voltage by 85 degrees. This is again in keeping with our general guidelines for largely inductive elements where current is expected to lag by 90 degrees. I'll return to this observation in a moment. Now, since we're being asked to solve for impedance, we divide the phasor equivalent voltage V by the phasor equivalent current I to solve for the complex impedance Z. Doing so yields Z equals 692.3 ohms at an angle of positive 85 degrees, where 692.3 ohms is the magnitude and positive 85 degrees indicates it's only primarily inductive in nature and most likely contains a small resistive portion. As we previously discussed, the impedance magnitude of reactive elements is frequency dependent, and as such, we cannot expect to find an inductor with an impedance of 692.3 ohms at an angle of 85 degrees at the inductor store downtown. If this is a purely inductive element, ordinarily we'd be able to directly algebraically rearrange the inductive impedance formula to solve for the inductive value that satisfies this condition. However, since we're dealing with a non-ideal inductor that includes a small amount of internal resistance, what are we to do? The easiest answer is to resolve the complex impedance value into its real and reactive components. Given polar format expresses complex numbers using a magnitude and direction, we should be capable of converting this to an equivalent rectangular format with real and imaginary components, where the real component is the resistive magnitude and the imaginary component the reactive magnitude. Doing so yields a real component of 60.3 and an imaginary component of 689.7. 692.3 at an angle 85 can be expressed using a rectangular format as 60.3 plus j 689.7. This implies that an internal resistance of 60.3 ohms is in series with an inductive portion that happens to have an impedance of 689.7 at a frequency of 70 Hz. Given we know the magnitude, in this case roughly 689.7, and the frequency, in this case 70 Hz, we should be able to solve for the component level of the inductor that satisfies this condition. Rearranging the inductive impedance formula to solve for inductance and substituting in our given values, we find an inductance value of roughly 1.6 henries, which by the way is a huge, heavy, almost fist-sized inductor. Problem solved. Before we wrap this example problem up, allow me to return to an important point. Recall we initially set up our phasor equivalence as I equals 52 milliamperes at an angle of 0 degrees and V equals 36 volts at an angle of positive 85 degrees because we stuck with the given condition that voltage leads current by 85 degrees. What if we wanted to employ the equally valid description that current lags voltage by 85 degrees? Using this description, our phasor equivalence would be V equals 36 volts at an angle of 0 degrees and I equals 52 milliamperes at an angle of negative 85 degrees. Note this version of the phasor diagram still shows a relative phase shift of 85 degrees between voltage and current, only this time voltage is our reference. It can be stated that current lags voltage by 85 degrees just as easily as it can be stated that voltage leads current by 85 degrees. Using either definition still results in a relative phase shift of 85 degrees. Does this affect our impedance calculation in any way, shape, or form? Absolutely not. When solving for impedance, we divide the phasor equivalent voltage V by the phasor equivalent current I to solve for the complex impedance Z. Doing so yields Z equals 692.3 ohms at an angle of positive 85 degrees. Exactly the same result we previously obtained. Let's try this again with a twist. Let's randomly assume voltage has a phase shift of positive 17 degrees. Given we've been told voltage leads current by 85 degrees, it can be demonstrated that current would have a phase shift of negative 68 degrees. Using this description, our phasor equivalence would be V equals 36 volts at an angle of positive 17 degrees and I equals 52 milliamperes at an angle of negative 68 degrees. Note this version of the phasor diagram still shows a relative phase shift of 85 degrees between voltage and current, only this time something else is our reference. This being said, it can still be stated that current lags voltage by a relative 85 degrees, just as easily as it can be stated that voltage leads current by a relative 85 degrees. Using either definition still results in a relative phase shift of 85 degrees. Does the use of an outside reference affect our impedance calculation in any way, shape, or form? Absolutely not. When solving for impedance, we divide the phasor equivalent voltage V by the phasor equivalent current I to solve for the complex impedance Z. Doing so yields Z equals 692.3 ohms at an angle of positive 85 degrees. Exactly the same result we previously obtained. What this referencing and re-referencing demonstration is supposed to illustrate is that absolute references largely don't matter, but rather the relative shift between voltage and current is of prime importance. This same circuit would always have a relative phase shift of 85 degrees between voltage and current, whether we used voltage as our reference, current as our reference, something else as a reference, or held it right side up, upside down, held it underwater, or tied it to a goat and threw it in a hole. Any way you look at it, there will always be an 85-degree differential between voltage and current. In summary, relative phase shift between voltage and current is of prime importance. We'll examine the repercussions of this observation when we discuss AC power in an upcoming lecture. Until then, that's it. Ordinarily, I wrap lectures up at the Big Bad Tech channel with a series of example problems for the user. However, I think I'm going to publish another supplemental lecture entirely dedicated solely to AC Ohm's Law example problems for two important reasons. One, this lecture is long enough already. Granted, we only did 9 illustrated examples. We took our time and slowly warmed up to Ohm's Law manipulations with a lot of general, relatively non-technical preparatory discussions. Two, this content is extremely important, sumamente importante, and you simply cannot perform AC analysis without having mastered, that's right, mastered AC Ohm's Law. Without overemphasizing its importance, AC Ohm's Law using phasors is the single most important concept central to AC circuit analysis, and you simply must understand it with no reservations for any further progress. If I was one of those teachers you see in bad after-school specials, I'd be like, don't worry, you'll succeed if you just believe in yourself, as I pick you up, dust you off, set you back on your feet, and make you a pancake breakfast. But I'm not. And I'm more liable to say, better luck next time, and just shake my head in disgust as you bleed to death in the dust at my feet. You simply cannot progress without absolute mastery of AC Ohm's Law using phasors. This being said, if you think about it, AC Ohm's Law as applied to AC circuit analysis scenarios is almost a direct copy of Ohm's Law as applied to DC circuit analysis scenarios. Really, the only thing we've added to our discussion is sine waves, complex number math, complex impedances, and phasor representations. If you had any issues understanding any of this content in this lecture, I will be so bold to suggest that your problem is not Ohm's Law per se, but rather synthesis of Ohm's Law with all the prerequisite content detailing sine waves, complex number math, complex impedances, and phasor representation. In short, don't show up to this gunfight with a dull knife. If you've got a problem with sine waves, complex number math, complex impedances, and phasor representation, now is the time to put these problems behind you, because if you fall behind, you will be left behind. If you need to revisit and review this prerequisite content, please take the time to do so now before continuing on to the AC Ohm's Law examples lecture. Alright, that's about it for now. In conclusion, this lecture examined AC Ohm's Law using phasors and complex impedances. We learned Ohm's Law is the fundamental cause and effect relationship of electrical properties and examined how it can be manipulated to solve for unknown quantities. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.